Do you have a solution for the first problem or not?
Not yet.
Not yet. But do you have a question? A difficulty or that? Okay.
So since the system is microcanonical.
Which system? The whole, yes. So the first problem, indeed, we talk about a microcanonical system, closed system. Yes.
So we just need to arrange the possible NI. No.
Okay, let's recall what is the first problem. Okay, you have a system of a multi-level system, right, with n particles. In total, we have n particles, which can be excited many times, but the total number of excitations was given k. So that so these are independent quantities that are given, and these are constraints. Then total energy is simply the unit of energy epsilon times sum of excitations, where I is going from 1 to n. Right? Sorry, did I use n in the notes? Yeah. Yes, okay. And this is simply this by constraint that we gave. The total number of excitations can be k, they're just distributed in a certain way between particles. We have epsilon k. Okay? So what's your question?
So this Ni is the occupation number for each particle.
But do you need really for this problem to know what is Ni? Does it matter at all? It's a microscopic quantity, right? We are trying to find entropy, which is a macroscopic quantity. So in principle, this Ni, as if you read this home assignment with the two-level system, you see that this Ni played no role. In fact, the system you don't need it at all to solve the problem. Okay, let me ask Ariel. Have you solved this problem? You have a solution.
Yeah.
Very good. Boris?
Yes, I have a solution, but I don't understand what you mean by multiple excitation.
Well, multiple. So, okay, in the two-level systems, okay, two-level systems. And I could be 0 or 1. That's why it's called two-level. Then, which means that each particle can be excited only one time. So you cannot have two is forbidden. You cannot have many excitations in one particle. What means? So this is multi-level. Now your Ni can be 0, 1, 2, even k. You can just k times excite one particle. So suppose, example, you have n equals 3 and k equals 3. What are, and this is multi-level system. What are possible configurations of this system? These are, okay, you could have 3 excitations in one particle, so this is n, 1, 2, 3, 0, 0. You could have 2, 1, 0. You could have 1, 1, 1. These are all allowed states. And if you have example of two-level systems, so again, same, n equals 3, k equals 3. So you will have really much, you can just see that the sum gives you 3, and there will be really many states as compared to two-level systems, right? Here, what you could have this, and that's all. There's no way you can excite 3 times a system in which each particle can be excited only 1 time.
Okay, let's take the first example.
What again?
Let's take the first example, 3, 0, 0. That means the particle was excited 3 times.
Yes.
And the energy of the system should be 3 epsilon, right?
Yes.
And if you consider, for instance, the one particle, it can be up or down.
I mean, what means down, up or down? Here is not, because the particle can be 3 times up, right?
Because if you consider, for instance, the degeneracy system.
Degeneracy system?
Maybe we have a many level of energy, and we choose one level of energy. This level can have perhaps 3 or n particles inside, which the sum can give us the same energy.
Yes, the sort of degeneracy here you have. So you can have 3 times this particle excited, right?
Yeah.
So you can consider that this is like 3 times the same kind of state has been excited, okay? And here, no state has been excited. In a way, these are, you can group them as being a state of excitation, and yeah, you can consider, I don't know, an electron in p orbital, okay? There will be 3 p orbitals, and you can put on each orbital by 1 electron, for instance, sort of these things. But I don't understand why you need it in this problem at all.
Is it okay? The particle can be excited 3 times.
Yes.
That means, first of all, the particle is excited. You have one particle. The particle is excited.
Mm-hmm.
And then, what happens after?
You excited 2 times. You put there in the particle 2 times 2 energies, right? So your particle, for instance, a gas, ideal gas, right? So this particle could have momentum 1, for instance, arbitrary units, and that would give it energy p squared over 2m, right? Suppose m is 1, that would be 1/2 energy of the particle, but it could have momentum 2, right? So your particle just moves faster, but it has more energy, and there is no problem for this particle to host more excitations, more energy. Okay, with p equal 2, you would have what, 4 over 2, it would be 2 are energy units. So you can excite the particle many times, but it's the conceptual problem about that.
That means if the particle is excited, we excite again the same particle which are excited again and again.
Again, yeah, so just you add more units of energy, so.
Okay. And then, in this case, what's the difference between excited with time and the degeneracy system?
I don't know. If you need to define degeneracy, you can, but right now I don't understand why you need to introduce degeneracy. Degeneracy is useful when you need to count something, and it's a concept that you introduce when you need to count states with degeneracies. But yeah, I don't need this concept at all. To solve this problem, you don't need, it's like an exercise, it's not real systems. There are like, example with channels. This is two-level systems, for instance, third problem, and the problem we considered in the course. But this is exercise, so this is your physical world, this is your solve. I don't think you need at all to think of degeneracy in this problem. It does not help you, not necessary for your solution.
Yeah.
Okay, let me ask those who are connected. Okay, Haya, are you there? Okay, can you tell so have you solved the first problem?
No, because it's very confusing. I haven't been able to solve it.
The first problem is very confusing. What is
both the problems are really confusing. Actually, I think I'm having trouble with the notation of everything. But I'm going to give it another try. Also, I haven't been feeling well, so I didn't really get around to it.
So can you at this time formulate what is your problem? So what, for instance, you say confusing, that means you think, you may think about something in two different ways. Does it mean that you have such kind of problem? Haya?
Yes, I'm sorry, I was muted. Could you repeat the question, please?
So you say you are confused, so that means that you are not sure how to interpret the problem, right?
Yes, so it's because, we started with the uniform distribution, then we did that, which is the microcanonical distribution, and then we went on to the canonical one. So I'm not sure which one to apply exactly. So I have to go back to
to apply in this problem. So, okay. So we have, so I give you a system for which energy and number of particles are fixed. Energy E, which is constant times the number of excitations.
Okay.
Okay. Then, for instance, what do you think is more likely, this state or this state?
I'm sorry?
What is more likely, for instance, this state or this state, if we consider this example with three excitations in three-particle system?
It could be either of the two.
So anything equally likely, right?
Yes.
So in which ensemble we had the equally likely states?
Microcanonical?
Canonical, right?
Okay.
It's isolated system, right? We get constrained the energy, number of particles, and no one can change this energy, and no one can add particles. So it's isolated system with equally likely probabilities. I think it's straightforward, leads to idea of microcanonical ensemble, just like we did in the course.
All right.
Okay.
And for the second one, for the two system one.
Sorry, we will go problem by problem. So you say about second problem.
No, I meant the second part of the first one.
The second part?
Yes. The two system.
Huh?
So problem one has two parts, A and B.
No, sorry. In the last lecture, I asked you to remove from problem one the second part. In the second,
okay.
I left it only for the second, and I sent you an updated list of problems, which now has three problems instead of two. But this problem one has now only one part, A. For the total system, you don't split it in parts. Okay.
I think that's where my confusion mostly lies.
That problem remains for the second. There is this part in the second problem.
Okay.
We'll come to that. Anna?
Yes. I have a question regarding the first problem. We can use the combination with repetition formula, but why repetition? I mean, Can I just use the blackboard?
Well, if you have, please.
Consider we have 3 levels.
Just a second. I hope this will help you. Okay, yes, continue.
Okay.
Yes, continue.
Well, let me draw here. We have 3 levels and 2 particles. So repetition means that I can go first to this state and then this is the first particle, the red one. And then, okay. And then to the other state for the first particle. That's the repetition that I can repeat 1 and 1 for the first particle?
Yes, yes, until you reach K states.
Okay, but it's repeating the number 1 to the first particle. Repeating
Yeah.
1. Yes?
Yes, yes.
Okay, that was the question.
That was all right.
Yeah.
Then if that question answered, can you solve this problem now?
Just using the formula for the combination with repetition for the count the number of states that I can remove from the total sample. Is the total sample?
Yes.
And then I calculate the entropy using the number of states. And from the entropy, I can calculate the temperature deriving it and the chemical potential.
Very good. Okay, I see that now you can. Ivana? Yeah, thank you. Anna. Ivana?
Hi.
Hi. So, how are you dealing with the problem 1? Have you been able to figure out your solution to this problem?
Yes, I had problem understanding the physics significance, but I think that now I understand.
Okay. Now I'm asking, who has who does not know how to solve this problem right now? Yeah. Okay, we agreed that we need to count just number of configurations, right? In this problem, so I don't need you to derive this formula, but essentially we have n objects, right? These are our n objects, and we have k things, right? Which we will put inside. Or, okay, another way to look at this thing, so we have collection of these objects, and we will choose, we can enumerate them, okay, and then we can choose, we need to choose k of them. So you take first object, and then you replace. So in two-level system, the first object was taken out of there, and there were only 2, 3 which you could choose second. But now that what is called repetitions are allowed. As soon as you took this object, we'll put another one in the line. So you still, when you second time choose your object, you still can take one again. Let's take one again. And then we'll take, one is again replaced, but as a third object, we'll take, for instance, object number 3. Okay, and we again, and so we do until in total we have chosen here k objects. Okay, when we have k, we stop, and then we just count how many one particle was excited, right? This is n1. This is N3. So combinations, we count how many combinations we can do by choosing k times n objects in which these objects will be replaced as soon as you pick one. That's a formula that is given by, again, binomial coefficient n plus, capital N plus capital K minus 1 over K, over K. That's it. That's the number of combinations. You expand this formula, and then you use Stirling approximation in exactly the same way as described in the notes that I have sent you. You expand, use approximation, simplify the expression to derive the entropy. And then I hope you understand how to evaluate from the entropy. Temperature is just, again, this problem, the typical problem solved in the notes. The only additional thing is to evaluate the chemical potential using similar ideas. Questions? Okay.
Why n plus k minus 1?
Well, it's combinatory, so basically you will have more, right, ways to choose this. There will be more combinations, just as we started already to. Now you can actually evaluate, right, how many in total here will be of combinations. It will be 3 plus 3 minus 1 divided by 3 factorial and 2 factorial. Okay, that is 6, 5, 6, sorry. Wait, sorry, that must be factorial. So it's 5 factorial over 6 over times 2. 5 factorial, what it gives us? 5 factorial, right? Am I right?
20 over 10.
Yeah, we can do right. 2, 3, 2, 1, 2, 3, 4, 5.
120.
10. Okay, there will be 10 configurations because you can excite many times the same state. Here, in two-level system, we have just one combination. So, how to derive this formula? I don't need you to derive it. It's combinatoric, so you don't need to know thermodynamics to do that. You can find online in Wikipedia some references, for instance, which show you how to derive this formula. But basically, I don't remember myself how to do it. If I sit down, maybe I can, but you don't need to do that. I don't require. But it's not bad if you learn a bit how to do usually this kind of problems you solve in probability theory courses, and then you forget and just remember that it's been solved.
So for the entropy, it should be written in terms of E and epsilon, E and K.
Yeah, so you will have K here, and then when you expand already this formula using Stirling approximations, you have to replace E over epsilon instead of E. That's it. Okay. Still, do you have it up? How to proceed? Read the notes. So basically now with having this formula, you just, at least to derive temperature, you will be able to do it just following the same steps as in the notes. Just step by step do it and you will derive the formula. Then there is just additional thing, you will need to find a way to find the chemical potential. All right, I think this problem, any other questions, okay?
Thank you. I think this has been very helpful.
Okay.
I understand now.
What?
You didn't call Said.
Said is not there. That's the problem. I would call him, but
Is there?
I don't see him on the list. So it's higher.
Sorry.
Is Anna, Ivana? I don't see Said. Stasi room. Maybe you are confusing with the Stasi. It's not Stasi. That's fine. Yeah, unfortunately, Said, yeah.
And also for this problem, and for two, I understand that it's microcanonical because of the constant energy.
Yes. Yes, microeconomical is, so all quantities here extensive, okay? As soon as you start to replace some extensive quantities with something intensive, that's where you start to get other ensembles. If you replace energy of a system with temperature, you get canonical. If you replace number of particles and energy by chemical potential and temperature, you get grand canonical. If you replace, for instance, volume by pressure, you get isobaric, or if you volume by pressure and energy by temperature, you get isothermal isobaric. Those are things where you start to replace some quantities by intensive, some extensive. But the basis of it all is microcanonical ensemble. Okay. Most of the, like in practical terms, you usually need anything but microcanonical. But the whole structure, the understanding and statistical properties of those ensembles, we actually start by considering microcanonical, as if your canonical ensemble is inserted in the world, which is altogether is microcanonical. Okay. So problem 2, just like the first problem, you can define entropy and yeah, entropy of this system, find temperature and chemical potential. You will have to find eventually. But then we decided to consider that's the thing. Now we can split our system. So we had originally so we are working two levels now. And we agreed that, just to simplify your life a bit, so there is n, but n is an even number, so that you can put here a wall and say that I'm now interested only in this part of the system, okay? Let's call this n, small n. This is small n, so that 2n equals n, okay? Now, I'm asking you to find entropy, first of all, probability, yes, of observing energy E. Let me put here 1. This is subsystem 1. What?
No, I have some questions on the probability.
Okay, then we want S1, the entropy of in this state, and T1. Okay, let's go. Jonas, have you made an attempt to solve this problem?
From what I try to look at it as if it's just two systems. Sorry, just two things wherein there is an exchange. So if E1 increases E to decreasing? Is it like that? So
first of all, let's recall. Yes, sorry. That's all right what you're telling, but I think we'll eventually come to a simpler thing, how to understand the system. Kyrell, I thought you wanted to comment something.
I have a lot of questions because I think what she means is the number of particles in the first one is dependent on the number of particles on the second.
This is true, but we said that we fixed, right? Number of particles will be fixed. What will not be fixed is, how many excited? Excitations will not be fixed. So K1, let me call it little k. So how many particles excited can change. There can be 2 particles excited here, and the rest will be excited there, but it may happen that there will be 3 particles excited and 1 less particles excited. So k can vary, okay? Lowercase k.
So,
yes?
So if you say probability of T1, is it the probability of T1 equal to some energy, or is it the probability that I have?
E1 is equal to, E1 equals, so it's, you can say that E1 is equal epsilon k, okay? And k may vary, right? Between 0 and capital K.
So it's equivalent to the probability that K1 is equal to K.
Yes,
Okay.
yes.
Okay.
That you observe a given number of excitations in the first subsystem.
Yeah.
Yes.
So I was thinking about there are 2 ways that you need to count.
Mm-hmm.
First is how many ways can you choose K from N?
Mm-hmm.
And then in how many ways such that K1 plus K2 is equal to K?
That's correct. Actually, that will. Yes, this is correct. You can do this thing, and like naive probability mathematics students will do, but you now know thermodynamics, and you could apply concepts of thermodynamics, which will be much simpler to solve this problem. But what you're saying is true. You can go down this path and obtain eventually the formula. The point here is that when we derived the zero flow, we did everything what I'm asking you to do here, but in the general terms. It happens sometimes that mathematical theorem for a very particular system is very difficult to prove, but for general case is very simple. What we did, we proved a general case in much simpler terms. Then you could do all these things here, what you have described, and find the answer, but it would be a much more tedious path, a way that is more difficult. Okay, Boris?
Yes. I use similar assumption. I said, okay, since we have 2 parts, how many particles is excited in the first part, and how many is excited in the second part? And so, okay, I define N1 in the first part, N2 in the second part. Finally, in the internal system, the number of particles which are excited is N1 plus N2, which allow me to have the number of all the possibilities we can have in the system. And actually, since we are interested in the first part, the number of possibilities should be the combination of N1 in the N1 in the total number of particles we have in this system.
Okay, take a chalk erase here. You can probably write down what you want to tell me. Can you?
Can I comment on something?
Yes.
Okay, so first of all, we have to find the probability, right?
Yes.
Okay, so isn't that just the microcanonical probability in this case?
Almost, yes.
So it would be.
First question: did you solve this problem yourself?
I tried to, yes.
But did you find an answer that you may doubt it?
I just got confused. I got really, really confused by the end of trying to solve this problem. But
Okay,
now that I look at it,
let me just ask Boris, then we will
okay,
come
okay,
to comments.
sure.
Okay, okay, if the chalk is too little for you, we can have a better one. Well, by the way, sorry, Karel, to find the probability, you eventually will need to do exactly these things. Yeah, yeah. I was already thinking about the entropy temperature, but okay. Yeah, let's agree to call this lower case and just. So this is omega of in the whole system or in micros? In the whole system. Okay, yes, agreed.
This is for the this system.
Mm-hmm. Wait a second. K1. Yes. Okay, yeah.
And then
Okay.
It's just K, right? K1 plus K2 is K. K1. So this plus this should give you this, right?
okay. This is the probability. Then
No, just replace K with epsilon.
fine.
So
The problem was
yes, so K1 is E1 divided by epsilon. That's it, right?
yes. Since we are this is the factorial.
Yeah. So E1 divided by epsilon will give you an integer value. So no, you can approximate it with Stirling formula too if you like, but
Stirling formula.
But I don't need for that problem. It's fine to deal with it in this form. Just replace K1 with E1. Yeah, that's it. Well, we could also replace K with E, but it doesn't matter. All right. That's the solution. Yes, that is right. Okay. Do you have a question about this solution? Doubt? Have you doubted that it was correct?
Yes, but I was not sure that it's correct.
Very good. It is correct. Okay. The probability. Yes. Yes. Sit down, please, Boris.
Sorry. I first thought of this, but I have some questions.
Okay.
I was confused with the omega E1. I thought you will still consider from the n taken K. I mean, before you could arrange or you could know how many ways you can choose K1 from n, from the small n.
Mm-hmm.
Isn't it that you need to consider how many ways you choose K from N first? Or
Okay.
yeah.
I think that is true. The thing, no, your problem is that you think that this would give two different answers, but the answer is no. They will give you exactly the same answer. You can do also interpret the, okay. Let me first comment this solution, then we'll see if you have still this question, okay? So the idea is the following. So we still know that all the system is microcanonical as it was before we put the wall. Nothing changed, right? The super system, so to speak, is microcanonical. And we know how to calculate the number of states in the total system, okay? Then we say, okay, let's fix the energy of the first system. Just, it can vary, but suppose I fixed it to K1, okay? And then that's exactly, let's just count how many ways this system could have this energy, okay? But if we fix the energy, we can make, it's the, again, problem of solving microcanonical system for this, but this time for this subsystem with lowercase systems. The only thing, yes, that the total number of realizations in the whole microcanonical, yes, it is still this number, and it will also be Cn of K1 times Cn of K2, okay? It's still the number of ways you can choose, sorry, K minus K2. We did this thing when we derived the zeroth law. The total number of states is actually the number of states you can do the first systems times the number of states that the second system can take in the meantime, okay? But, so you can approach the system as you say, let's start just to draw the number of K1, but that's goes down to how many you can take configurations here, I believe. So the way Boris approached the problem, I think the simplest one, just fix K1. And let's see how many ways you can obtain K1 in this subsystem. The whole system lives still on its own, and therefore the total number in the supersystem of configurations will be this. But we're interested just to see for this particular value of energy in the first system, how many ways we can combine excitations in the first subsystem to get this value of energy. It's just a fraction of the total number, okay? Those who are connected online, since we already solved this problem, can you just ask questions that you have about this part of the problem?
Well, this is how I solved it as well. This is what I was going to say. Before
right.
Boris solved it, so, but I got confused after that whether it was right or not.
Well, that is right. Okay.
Okay.
Anna? Ivana? Okay. Anna, can you comment?
For computing the entropy, you need to use the first relation, the K1 plus K2, plus K2, Spanish.
Wait a second. I'm asking about probability right now.
The probability, yes. I started with the energy instead of that.
But do you understand?
But it's the same. Yes, it's the same.
Okay. Ivana? Questions about it?
Yes. What happened when K is greater than N?
It's not possible. In two-level systems, it cannot happen. So, in the sense that the probability of finding such a system is zero, because you cannot find any combination of single excitations that will lead to K more than N. So the probability is zero.
Okay.
Okay. Number of ways you can create such a system is exactly zero. Divided by the total number, whatever it is zero. Other questions? Okay. Okay, Anna, let's begin this time with you. You were asking about entropy. So how would you approach solving entropy of this system and defining?
KB logarithm of the number of states, but I don't know if we have to use the first one, the first line of Boris.
Yeah, so the thing is that Boltzmann entropy, okay, Boltzmann entropy can be defined for any state. So you can define Boltzmann entropy for E1, and then
Use
the entropy
your estimation.
Yeah, so omega of E1 times KB. So in fact, in statistical physics, you often will find that people computing Boltzmann entropy of a non-equilibrium state. Okay. In the problem, so that's correct. If you want to estimate the entropy of energy one, this is fine. Before going to the to that question of entropy, I however was asking you to, so the problem one, find probability P of capital E1 of a macro state with the first subsystem's energy E1 and its entropy. The entropy is this, okay? You can define Boltzmann entropy for a given number of states. Now, in thermodynamics, we agreed that we, in classical thermodynamics, we have we consider only equilibrium states. So, if E1 equals A, like all excitations went into the first system, is very unlikely state. I think you intuitively understand this, right? So, if we want to speak about classical thermodynamics, eventually we will need to take average, or in terms of ensembles, we also can speak of the most likely state, okay? And here I have been asking you, can you find the equilibrium energy of E with bar before you proceed to evaluating the temperature, okay? Why? Because in classical thermodynamics, you can find state functions only when you are at equilibrium. You can apply Boltzmann formula, but in classical thermodynamics, it does not make really sense to speak of entropy of system when it's not in equilibrium. Equilibrium, according to the ensemble approach, is the most likely state. How to find the most likely state? Anna?
Just deriving the entropy.
What to do with entropy?
The derivative of the entropy.
No, we derived it. It's over there. S1 is equal to KB logarithm of
A differentiation in English.
Why do you need a differentiation? I mean, the final goal of your differentiation would be what?
Equals to 0 because I need to maximize entropy.
That was a condition of for what?
For the most likely.
Yes, for most likely state. So most likely state is by definition is maximum probability, and it's eventually also a maximum of entropy. Okay, so these things coincide, and that's why we try to find derivative. But very often, before you start doing any calculations, is very good to try to intuitively, physically, what the intuition says. What is the most likely state of energy if it's split in half?
One who has the most configurations, the many.
No, that's the definition. I'm asking you. So I give you constraint. This is E. What is, in your opinion, E bar, the equilibrium energy in the first subsystem? All right, Kyle was very eager to answer. What? No?
I'm getting
So
I can answer this one.
yeah, I.
Okay, so we simply use the formula for entropy that you've written, but instead of omega E1, we just substitute combination, the omega E1 that Boris wrote with K1 and N.
Okay, that's true. That would work. So what I'm trying still to push you towards is you already know how to use probability theory. Now I'm trying to push you to develop your skills of statistical mechanics.
To have the same number of excitation from the state 1 and the state 2?
Yes. So first of all, we are speaking of equilibrium, okay? Which equilibrium? What is mechanical equilibrium? So if I take like a symmetric pen, like equilibrium that it will stay on one side is when all forces are equal, okay? So you have a system that's split in half. It is obviously symmetric. Probabilities, they usually follow, like right in the coin. If the coin is fair, which means both sides, it will be half and half, right? Because it's symmetric. All probabilities laws in physics, they all follow the symmetry. So if you find that something you think is symmetric, but for some reason, in fact, that's already an answer. So if you find that the thing gives some preference to, so energy for some reason accumulates in one system, that means there is some asymmetry. So there is a reason why half of the system tends to have energy. Right now, this half of the systems, they are, for what you know, for information you've been given, entirely equivalent, right? So equilibrium should be something when things are symmetric, or at least forces, thermodynamic forces bar.
Okay, now I'm confused again. Yes, I am confused again. So will plugging in the value give us the answer or not?
It will give you the answer, but what I'm trying to push you also to think about before doing math, just try to think, to imagine what will be the final answer.
Okay.
So it just helps you to guide you to where you are going, okay? So it's already, even before you do any calculation, you already can make sense of this problem. It's totally symmetric. Half of the system, well, first half of the system is entirely equivalent to the second half of the system. Equilibrium, the most likely state is when both systems have equal number of excitations. There is absolutely no reason in this problem for why one system must have more. That's, so to speak, your final goal. Now you start doing math to prove that. Okay?
Yes, thank you.
And yes, you can plug in again. I tell you, probability theory will work. So you just plug in expression for PE, like you can use instead of factorial gamma function, do differentiation, all this sort of thing to finally find the answer. But in the course of lectures, we already solved the final answer where we didn't know anything about the microstates of the system. And we found that the condition was that entropy, so recall the problem where we put in contact two systems, right? So we found the condition of equilibrium, which states that derivative of entropy with respect to energy of one subsystem equals to the derivative with respect to energy equals to the second subsystem. Okay? Then, what does it mean? So that entropy of the first system with respect to energy equals, we derive this condition, okay? At bar, okay? So it's true, if you take the formula that Boris showed and you do all the calculations, you will eventually find to this very same thing, but with a lot of n factorials and so on. Instead, you can just jump there. That's why statistical mechanics is so useful, that you can avoid doing tedious calculations, just jump to the final conclusion. You already know that the entropy is maximizing the probability. So maximize the entropy. What is the condition? Zeroth law. That, okay. So what we need to find is the simple form of entropy, right? And okay. Now.
So do we equate this to 0?
No. The condition to 0 was that ds1 over d1 d1 minus ds2 d2 over d1 equals 0. That's what we derived in the class. That was the condition that maximized
Yes.
the number of states. So this must be just equal, okay? Now, what we need is to find the convenient form for S1, okay? So in other words, we need to evaluate this logarithm AKB of omega 1, okay? And you see, so probability of E1 was this number divided by E2. For the entropy here, we just need E1. And it looks just exactly as the two-level system, right? So you can go to the notes and pull out the formula for S1. What was the formula? Can someone look it up? It's in the notes which I sent already.
It's long.
Yes, but isn't it this? Is it the one after the Sterling's formula?
Yes, it's equation 4.19 if you have the book.
Yes, but that's what I'm saying. But that is so. Before applying the Sterling formula, we still had the formula with the combination that Boris wrote on the
Yes, yes,
board.
yes.
So it's kind of the same thing.
Yeah, this formula that
Yeah.
we got one, right? But you saw that it's exactly the same formula. It's just instead of E total, you substituted E1, right? Nothing has changed.
So we just
Well, okay, let's
what do we do then?
keep equation 419. We can already go to equation 420 instead and to find the temperature, right, of the first system. Higher, do you agree?
I agree, but I'm just trying to understand that don't we have to find the entropy as well?
Well, you can just copy formula from there in your answer and say that by replacing E with E1 and capital with a small lowercase n,
Yeah.
okay, that is pretty straightforward. So
Okay, so that is correct, right?
just realize that it's exactly the same formula.
So but it's correct, right? That answer is correct.
Correct. Why not? We read the
Okay.
This is Boltzmann answers, right? By
Okay,
definition,
great.
apply the definition, right? And then, yeah. So and then what? This just says that T1 equals T2, right? Okay. Then let's take the formula.
Yes. So we will just use 1 over T formula.
Yes. Yes. So it's minus KB. I'm just reading the formula already.
Yeah.
With minus sign, right? It's there. Logarithm of
E over N epsilon.
E1.
Yeah, E1. Yeah.
And epsilon minus E1 equals
E2. Sorry, same thing, but with E2.
With E2. Yes.
Okay.
E2 divided by N, because we agreed that we split in half, right? In principle, I could put N1 and N2, but let's go to E2, okay? This will go away. Now we solve this question. You ask me, what is E? Given that E1 plus E2 equals
Won't that just be n epsilon divided by e to the power epsilon Boltzmann constant into temperature plus 1?
Let's remove this, right? Logarithms with KB, we remove. And what we get? That E1 times n epsilon minus E2. Sorry, I better start writing somewhere else. E1 times n epsilon minus E2 equals E2 times n epsilon minus E1. What did I do? I just multiplied both sides of the equation by the denominators, right? And then I open the brackets. We have E1 n epsilon minus E1 E2 equals 2 n epsilon minus E1 E2. This will cancel. This will cancel. What do we find? E1 equals E2. Given that E1 plus E2 equals E, you will find that the condition of E bar.
I just have one question about the energy. We still have to find the energy, right? Like a value for the energy.
Yes, this E bar.
So isn't that given by the next formula, like 4.21? Is that the correct formula?
No, the energy is over here. This is E bar. We just found the condition. So this equation will give you.
I'm talking about E.
Capital E.
Yeah.
For the whole system, it's fixed. Yeah. What?
Yes. But, do we have to find a value for E?
How do you can find it?
It
It must be given by the condition. I can give you 25 and whatever. The rest is all. So if E is equal to 25, I could give you 25. That would be 25 5 over 2. The most likely energy value in the first system. If it were 30, it would be E bar would be 15. Okay.
Okay,
E,
okay. Okay, so that's the initial, like, okay, I get it. I understand now. I got it. I got it. Okay.
Find its value from the data, which from the problem. It's a condition.
Okay, okay, thank you. I understand.
I think you're a bit speculative.
I was confused because I was so confused. It's like clearing up now. I just wanted to clear out this confusion. Thank you.
Yeah. By the way, right now you see for simplicity, I gave you that lowercase n. So basically, the system was split in two. But I could equally likely ask you, for instance, we have n particles and in the whole system, but I could divide it in 3 and take any part. And you would be still able to find what is the most likely energy. Okay? Just using these formulas. Of course, you could do this the probabilistic way. You just start with factorials, take the derivatives, and go all the down way. You would find the same answer eventually. Because when you solve, a specific concrete problem, you focus too much on details. But if you go to the theory of thermodynamics, you see the problem, from a little far, but you're doing exactly the same operations at a little bit more abstract level, but the formula will be the same. So finally, you will still find that this will hold. It's just you will do a little bit more work, and it would be only applicable to this particular problem.
Okay,
But you see that it works in general. It will work if you work with energy in two-level system. If you speak of bytes in the computer code, it will work. Information theory, finances, wherever you can come up with a model where you can define energy function, it will work. Okay?
Yes, thank you.
Okay. Then chemical potential, that's already on the list. Okay, but let me give you a little more. So here we work only with basically microcanonical stuff. Again, thermodynamics works only when you find this E bar. That's where your classical thermodynamics works. For other values of energy, it's not equilibrium. So classical thermodynamics is not applicable there. You don't know how to deal with these problems in the context of thermodynamics. One more thing. So. So we found that 1 over T1 equals 1 over T2. What do you think about the whole? If I use the Meran-Kardar formula for temperature for the whole system, that's for the whole system, not for the half, will it be equal to T1 and T2, or it will give me a different value? So Meran-Kardar solved the problem for the whole system of n particles. We solved the problem for subsystem, and we found the formula for temperature, which you have to write down. But if I put numbers there, will I find T1 equal T2, some number? And if I use Kardar formula, I will find another number. Will this another number be equal or different to this 1 over T1? Who can answer this question? Okay, Anna, what do you think about this from physical grounds? Okay, try to start using your physical intuition. What do you think about the whole system? No, better, Ivana was omitted. Sorry, Anna. Yeah, Ivana was participating a bit less. Ivana, can you connect your microphone? So, Meran-Kardar found this formula. Minus KB over epsilon logarithm of, can you read it to me, please? I raised it.
Over
And minus E? Yes. Okay, and we found this formula. E1 and epsilon minus E1. So, if I put some real numbers, will 1 over T1 be different from 1 over T? Ivana? Ivana?
Yes.
What do you think?
Can you repeat it, please?
So,
the question.
Meran-Kardar found temperature for the whole system consisting of capital N particles, two-level system with N capital particles, and energy E. We then solved the problem where we separated system in two halves, each half having n lowercase n particles and energy E1. Actually, sorry for that, E bar. We have to use in the formula E bar. We cannot use E1. That should be E bar, the equilibrium energy. Now, question. If I put real numbers for E, N, E bar, like real numbers, 3, I don't know, 10, whatever comes consistent with the constant, will 1 over T1 equal 1 over T?
If the system is in equilibrium, it must be the same temperature.
Yeah, so the temperature of the whole system should be equal to the temperature of subsystem. What do you think?
Yes.
Yes.
Yes,
Not
because it's in equilibrium.
Okay, that's easy to show. We can show from this equation. Since we already found that E bar equals E over 2. Can you show this? Yeah. Okay, Carol. Yeah, it will be halves of the cancel, right? This half, this half, this half. They are equal. So your physical intuition will work. It really is, you can behold that all these things, abstract things that we did in the lecture, it works when you solve like really silly problems and even not silly problems, it will still work. Now, we have discussed that actually, right now we were considering halves of the system, but actually I can say that I give you N1, and it's not half of the system. Okay, so I put here border, this is the system I'm interested in, and I don't know how many N. Okay, I don't know how many, for instance, I know I don't tell you, but I use the formula for temperature, this one, and I give you temperature T. Okay, so I tell you the temperature. I don't tell you capital N. I don't tell you K. That is E. Now, can you find me a probability of this thing? Energy E1 in the system. Yeah. Yes. Hi.
Shouldn't okay, so are these two, is this the same case, right?
Yeah, the same case, but almost the same. So I changed only the idea that now this N1, which is N, but it's not anymore half of the system. It's just some part of the system, of the whole system. So it is not equal N over half. It is not anymore N over half. So the whole system still lives in the microcanonical ensemble, but I keep secret what is the total N and total E. Although I can use this formula from Chardar to find temperature. And I will give you the temperature. Can you find me probability of observing E1? So first of all, we are working now in which ensemble?
So you're giving us the temperature.
Yeah.
If we know the temperature, then we can calculate E1.
Yes.
From the equation 4.19, I think.
Yes, yes. So you use this, yeah.
Yes, yeah, from that equation, yes. So
yeah.
Then we have E1, and once we have E1, but we still don't know N.
You don't know N?
Okay. I have to think about this.
No, you knowing, right? Anyone is knowing. Or knowing. Since you know that we are your system have N1 particle.
Yeah, you know this.
Okay. And we can use to find E1.
So you see what pass I make. So before we had okay, NBE ensemble, the canonical, right? Well, V is hidden in the system. We don't have really V. But then we pass to from microcanonical ensemble. We flip E to the T. Okay, now you don't know.
Is the canonical ensemble?
It is canonical ensemble now. Okay.
Because the other is like considered as a thermal bath.
Yeah.
The other.
So it is canonical ensemble, very useful formula, for instance, Boltzmann statistics. So if I say that I excited this state and this state, how to find this probability? Even I don't know now the total now I do not know, right? Omega E, I do not know. But what I can use, Maxwell-Boltzmann formula, right? So this microscopic configuration, probability of observing these two particles excited, is just the energy of this configuration divided by sum over all, exponent. E of mu over KE. Okay, overall configuration. So what you need is just to know all possible configurations in the system. And now you would also be able to compute entropy using the partition function. Okay? And the formula, like, this is what tells you thermodynamics in general. If you go down to details, you will find this formula useful, right? So that you can relate your temperature to your equilibrium energy. Okay, so you can do all calculations for equilibrium energy. You can also do calculations for microstates. Even though you don't know how large is your system, what is going on there. It could be infinite and whatever. But without like going down to details, thermodynamics and statistical mechanics already tells you how to deal with this problem in very graceful manner, which is quite simple. So the main point of this exercise is actually for you to feel, right? I know you can use combinatorics and so on. For this problem, yes, but when you go to do research on a real problem, probably it will be already, sometimes it's still possible, but often very complicated. Just to do some magic with thermodynamics, sometimes you get an answer much faster than trying to think deeply about all these possible microstates and so on. Now let me see. Yeah. Partition function, very convenient object. If you can find it, you can find everything in a much faster way. Instead of trying to compute the number of states, here you can just measure the energy and try to differentiate. Yeah. Okay. Do you have questions? No? Everything's clear? Yeah. Yeah, probably, I don't know if John will give you exercises, so I don't give you all the exercises with canonical, but I'm sure down the course you will, actually, canonical ensemble is the exercise problem 3. So if you missed the point that the assignment was updated, please find another email where there is updated assignment with the problem number 3. Actually, it's also two-level systems, channel open, close. In the class was also 2-level, but I give you like 3-level systems. There you can use canonical ensemble very easily. Yeah, so the main point is that there is probability in statistics, okay? But in many situations, physics, and sometimes not only physics, finances, you can just find analogies, okay? You can call something energy, like, I don't know, money in your purse or some other good quantity that corresponds to energy. And then if you can, find parallel, map your model of ensembles to interpret it in terms of real or physical or non-physical problems that you study, once you're done, you can apply all these methods. You don't need to evaluate all these configurations, because eventually you will end up with reproducing exactly the same formula, but go in a complicated path. You use a little more of ideas of thermodynamics in there. All right? Now, since no one has questions, we didn't make any breaks, I think it's good time to stop here. I still wait for you writing down, or like I did not derive the formula for entropy, but with Stirling approximation in the first problem, so apply it just to get a little gist with the Stirling approximations and write it down and send it to me still, that I check it down. And problem 3 is still on the list.
I have a question from the problem 3. Like for the figure plot, we should do like two curves on one plot.
You can put both curves in one plot. Just it's
And
nice.
the conditions are to have the limits for e equal to 0, like limits. We have to calculate limits of the function.
Limits. I don't understand.
They say
No,
of this function for e equals to 0, delta e
yes,
equals to
I need
1.
to just numeric value, because to put something on the plot, you need numbers, right? You cannot
Okay,
put
that was
right?
my question.
So this number e equals 0, which does not matter in that problem. What matters is delta e, right? And I give you values for that.
Okay, thank you.
Just to be able to plot it with some numbers.
Okay, thank you.
Other questions? All right, I hope that was useful and you get a little part of this information shot at you in 1 week and in your heads with this practical exercise. Okay, if any questions, just come write me email.
I have a question.
Yes.
I'm a little confused because I don't know if my partition function of the tree problem is right.
Partition function in problem 3?
In problem, yes. Because I was discussing with Anna and she got another answer and I got a different partition function, and I don't know why, what of them,
okay, what partition
which
function
of them are, I don't know how to write it, but I can email you to show you my partition function.
Okay, yeah, you can send this email, by the way, to the whole group of students. We can discuss your question by mail, since you are not able to go to the blackboard and write down your idea. We can discuss, like, create a new thread on email, right? Problem 3, and send it to everyone. Then we.
Yeah. I think that the problem is when there is the closed channel, it should occur E1 and E2 simultaneously. Like you have to multiply both probabilities. You have
What channel?
the problem 3. It says that we have 3 possible states with 3 energies. So the ion is closed when it is in the states E1 and E2, like simultaneously. I mean that I have to do a product of the exponentials.
In partition function, you don't have probabilities, right? You don't have probability in the partition function. You need partition function to find probability. But partition function, canonical, right? You need to use in this example, is a specific thing. That is, probability for that thing you don't need, right?
Okay.
Wait, so I wrote it down here. Do I need here probability? No.
No. Okay, thank you.
So I just need energy of a state and a way to enumerate all my possible states, right? To find such a good R, or maybe 2 I and J indices if your system is many dimensional. or integral if your system continues, or double integral if your system continues but has 2 degrees of freedom. You need to find a way to enumerate your states, and then you just need to take some integral over all energies and use them
Okay.
a specific Boltzmann factor, right? Boltzmann factor is called. Okay?
Okay.
Yeah, I think I would be surprised if you were not able to solve the third problem. Maybe this session was useful, for jamming you towards thinking not the way you already use, because it's always very useful to think the way you used to think, right? You already studied probability statistics, and then it's always much easier to recall this knowledge, to invoke it, than to study something else or to acquire new skills. But right, for these simple problems, you can do that. For other problems, you won't be able to do this thing, and therefore it's very important to develop new skill, applying structured thermal analysis. Okay, that also makes your analytical skills wider, broader. Okay. Other questions? So, Ivan, I wait for your formula in the thread. Create a thread, send email. We will discuss it through email. I think it will be simple question to answer also in writing. Other questions before we stop? No. All right. Thank you. Thank you. Yes. Goodbye, all those who were connected with us online.
Okay, thank you.
Bye, Professor. Thank you.
Thank you.
See you. Boris, I have a question. Do you play soccer?
Soccer.
Football?
I have played.
Yeah, because we have ICTP team. So we have, first of all, friendly matches just between us, but we also have our team participates in an amateur league. If you are really a fan of soccer and you like to play, you can join us.
Okay.
If you're interested, just email me. I will give you the coordinates. So we use WhatsApp to arrange meetings and so on. If you like to play soccer in Trieste, let me know.
Football.
Yeah, football. So soccer in the English term, but football.
Okay.
Yeah.
And how much can you have tools for that? Yeah. Seems.
Shoes. Which size do you have?
I just bringing this kind of tools.
No. We have shoes in the league. If you play well, you can join us. We have shoes. Actually, true, but we not all sizes. So I'm asking, what size do you? 41, 43.
Yeah, 41, 42.
41, 42.
Yeah.
And maybe difficult. Well, that's the size I think that we don't have actually. I will check. But yeah, let me write an email if you're interested. I mean, it's not obligatory,
I'm getting one. I will send you an email.
Okay.
Okay. What is your office?
Do you know our section? Where's our section? QLS. Do you know office of Antonio?
Not yet.
Not yet. So you need to go. So when you go down, there is a tunnel.
Yeah.
So you take this tunnel, and then there will be elevator. You go to floor number 2.
Okay.
And there you just from elevator you go to the right and look for office 213. Okay. I hope that helps. Yeah. It's easy to show, but yeah.
Okay. See you.
Yeah. See you.